Strong law of large numbers. S stands for strong. Let's say, let's write here a strong law of large numbers among many. Let's prove one version of, or one strong law of large numbers. What does this strong law say? Assume x1, x2 are random variables now in L4P. So we assume that we have finite fourth moments. And let's assume that our random variables are independent. We assume that our expectation of each of these is the same, mu, for all j. We assume that we have a fourth moment of each xj. That would be the L4 norm. Let's assume that it is bounded by a uniform constant k4 for all j. Independent random variables, constant mean, bounded fourth moments. The claim is then the average of these random variables. If you think of j indicating time, so this is a time average. The time average of these random variables converges to not any x, but the constant mu. It is true in probability. Actually, by the weak law of large numbers, we know already that this is true in probability. So that would be weak law of large numbers. But in this case, we get stronger. So what makes this strong is that this is true almost surely. How could we prove such a stronger version of the convergence? That if you look at this task, it looks actually quite demanding. And it is. So it's something that I believe it was not proven in the 1800. Maybe it was only in the early 1900 when the first proof of this thing saw light. Let's investigate this proof. Here we have a quite elegant proof. If I recall right, this was invented by Kolmogorov. So proof. Let's make one simplification. Assume that mu is equal to 0. It's a constant. Let's assume that we normalize things so that this constant is 0. It helps us with the notations. And as before, let's call this thing here. What we have here, this sum, let's call it Sn. And let's call now E the event that we look at. So let's call E the event where 1 over ns n omega now tends to 0. And our claim is that the probability of E is 1. That's what we are claiming it. Okay. So E is our target event. And now comes the kind of clever trick. Let's look at E prime as the set of omega for which the sum from n from 1 to infinity S and omega divided by n to the power 4 is finite. This E prime looks quite strange. If you look at it, okay, it looks like, okay, it should, E prime has nothing to do with E. But let's be careful. Let's see. What if omega belongs to E prime? What happens then? Then it so happens that these fourth moments here, we have an infinite sum of non-negative terms. So this sum is finite. positive sum is finite. It can be only finite if these terms tend to 0. Yes. So then S and omega divided by n, these terms must converge to 0. But if the fourth moment converges to 0, so then it follows that also S and omega divided by n. This also must converge to 0 if omega happens to be in E prime. So what it means that then omega actually must be in E as well. Yep. Does it look sensible? So what this thinking reveals is that this E prime is a subset of E. And actually our claim, what we will prove is that also the probability of E prime is equal to 1. If E prime has probability 1 and E is a bigger set, so then of course the bigger set must have probability 1 as well. And then we are done with the proof. Why does the bigger event has probability 1 as well? Look at the complements. If somebody has probability 0 and you have a smaller set, then that also has a probability 0 by the monotonicity of probabilities. So what we plan to do is to prove that this E prime has probability 1. And to investigate positive sums, actually what we are going to prove is even stronger. So actually we are going to prove that the expectation of this sum is finite. If the expectation of this positive random variable is finite, so then this random variable must be finite as well. So actually this claim will imply that one there. Imagine that this positive random variable that we have here inside the parentheses, if this might have some positive probability of taking an infinite value, then this expectation would be infinite as well. This is part of the Lebesgue integration theory. That it's sufficient for here. We prove that the expectation if something is finite, so then this thing is finite as well. Okay, so that's why this is no more a claim. The real claim that we look at is here. We look at the expectation of these fourth moments. Then what? Let's use how Fubini helps us here. Fubini helps us if you think of the sum as a counting measure, counting elements, and this is a probability measure. So actually, the expectation of the sum Sn over n fourth, we can think that, okay, this is actually a double integral. So we are integrating over omega, and then we are actually integrating over the positive integers. We are integrating the function Sn omega divided by n. And here the sum is actually, we integrate it with the counting measure. So let's say this is the counting measure of, and the integration variable is now the n here. If you think we are counting with respect to n, so that means that we are integrating with the counting measure in n, and then that's what we do inside. So this is a funny way to write this sum. I forgot the fourth moment, but that's there. And then what? Let's try to make a bit of space here. Then what? Then we have outer integral integrating with the probability measure because we are taking an expectation. So we have double integral. What we are integrating is non-negative and measurable. So That's why we can use Fubini to change these measures, and we integrate with n first and then with omega. So the inner integral becomes the omega integral. And if we write this back in the kind of normal common sense notation, so then it becomes sum n from 1 to infinity expectation of Sn divided by n fourth moments. Okay. That was the Fubini kind of contribution here. If you have questions here, please ask. Otherwise, I clean it away. I will clean it away. And actually, from now on, we can remember that whenever we have expectation of non-negative sums, so we can always think about Fubini in this way, and we just interchange the sum and the expectation in this way, that the sum goes here, the expectation goes inside. So then we have actually, then we can take the constant 1 over n fourth in front and expectation of the fourth moment of Sn in this way. To analyze this thing and finish the analysis, we need to calculate what's the fourth moment of the object that we study. Let's recall. We are looking at this Sn, the sum of independent random variables, and we want to calculate the fourth moment of this. How do we do it? Well, we have the fourth moment of sum I from 1 to, or let's say j here, maybe. Yeah, it was j. So the fourth moment in this way. Let's take the expectation actually away for a while. And let's see how we can use a bit of algebra to reorganize this fourth moment thing. So you might think that there's a sum from I, xi, then there's a sum from j, xj, there's sum k, xk from 1 to n, and sum of l, xl from 1 to n. In this way, we can write the fourth moment of the sum, and then we can bring in the sum indices in front. So we have I, j, k, l, xi times xj times xk times xl, right? Now we can take the expectation of everything. So we put expectation there, expectation finite sum, it goes there. We get the expectation of this thing here. Okay. Then we recall that we assume that mu is 0. So that means that expectation of xi is 0. We also recall that we assumed independence. So can we factorize this thing to independent? Can we factorize these expectations to independent things? What we want to do is to actually to write this as ij kl sum, expectation of xi, expectation of xj, expectation of xk, expectation of xl. We would like to use independence and factorize. Can we do this? Is it okay to do this? What do you think? Independent random variables, do they factorize? Give me green if you think that this is fine to do because we have independence. Give me red light if you see something suspicious here. Somebody think that this might be okay. Morally, those who say yes, morally you are right. But those who give me red light, you may be morally right, but you might be technically right as well. Namely, there could be common indices. There might be I and j being equal, and those equal indices might actually contain some terms where I and j are equal. So in that case, we cannot factorize. We get xi squared here. So what we need to do here is be careful about these I and j indices which overlap each other. And to do that, we could say that, okay, there are these terms where these guys don't overlap. So let's write ijkl. Let me write prime here. Expectation, xi, xj, xk, xl. And prime means here distinct indices. But then we have other terms. So we have overlapping terms. So we have terms such as, for example, those terms where we have two different values, I and j, let's say distinct I and j, and we get terms such as xi squared and xj squared. We need some constant here that tells us the combinatorics. Then what else we have here? Okay, the expectation needs to be there because it's there. So we need that there as well. Then in the sum, we get ij pairs where xi occurs 3 times and xj once. Again, we need some, this is constant 1, so we need constant 2. The expectation is there. What else can we have? We have some terms with 3 quantities, 3 distinct indices. So let's say prime for distinct expectation. Let's say I is 2 times, then we have j once and k once. That's it. And do we have some other constant still? Yes, we do have one more. So what else is there? There's the one case where all of these are equal. So we have just I and we have expectation of all are equal, xi fourth. Right. Then we need some constant C3, C4 from some combinatorics. How many times these kind of repeating indices occur? And that takes a while to calculate, but I think if you take a bit of thinking, depending on how fresh your discrete math skills are, so it may take a short time or long time, but I assume I did this yesterday and my calculation gives me 2 here, 4 here, and 3 here, and 1 here, and 1 there. So these should be the combinatorial constants. I think these agree with the lecture notes, so I believe them to be correct. Anyway, they are just constants which we don't care so much about. What is now important is that if you look at this, I, j, k, l, these are all distinct. Now, because they are distinct indices, the expectation factorizes inside these. So we get expectation xi times expectation xj, and so on. Yep. So instead of writing this, I can take the expectation and factorize this thing in this way, that we have expectation xi, expectation xj, expectation xk, expectation xl. But then we assume that all of these, each has expectation 0, so this vanishes 0, 0, 0, 0. So there's nothing here, just 0. In the second one, we have expectation factorizes with these, so we get expectation xi squared, expectation xj squared. Yep. Here we factorize expectation xi third, expectation xj, but this is 0, so that one is deleted, and what we have there is 0. Here again, we have expectation xi squared, expectation xj, expectation xk. These are zeros, so this is 0, 0, that vanishes. So what vanishes is let's clean up whatever vanishes here. The first thing vanishes, so we take it away. The second one does not, and third one did vanish, so let's take it away. The fourth one, there's nothing here, so let's take it away. What do we have left actually is only 2 terms. Yeah. So we have this term here. Let's put it there. And then we have the other term there. Let's bring closer here. And then what? This is I from 1 to n. This is from 1 to n as well. So this is less than n times we had the universal bound on the fourth moment, so that was the K4, let's recall. We assumed that we have universal upper bound K4 here. Yeah. So we use that bound to bound this sum with n times K4. Then we have 2 times second moments. Can we bound them? We used Cauchy-Schwarz or Jensen, and we have, okay, we have n times n minus 1 entries in the sum, and then these are less than, I put square root expectation of xi fourth. So that's what we can do with Cauchy-Schwarz, and then I put square root of expectation, and then I square inside. So with Cauchy-Schwarz or Jensen, so you can do this thing. And this is n times K4 plus 2 times n minus 1, and then K4 square root. So that's also K4. What do we get? We get K4 n plus let's see. Maybe this 2 should be 3, okay, but if it's 3, so we can correct it later. Let's think about it, believe that it's 2 now, so let's not worry about it. So we have 2n squared minus 2n, okay. And then this is less than 2k4 n squared. What did we do? The fourth moment of this Sn is less than something, constant times n squared. So we prove that expectation of Sn fourth moment is less than a constant, let's say constant times n squared in this way. So what happens? Expectation Sn fourth moment n fourth is less than c times n to the minus 2. If we sum this from n1 to infinity, we have sum less than n1 from infinity, constant times the sum n from 1 to infinity n to the minus 2. Well, this is not the harmonic series, this is something which is decreasing faster, so this is actually a finite thing. We have proved that the sum of the fourth moments divided by n fourth is finite in expectation. Because it's finite in expectation, we know that this is okay, this claim. It's finite in expectation. We have that E prime occurs with probability 1. This is finite with probability 1, this sum. And now we know that its terms must also go to 0 with probability 1. So with probability 1, things go to 0 there as well. We are done with the proof. Under the special assumption that mu is equal to 0. What if mu is not equal to 0? We need to do a bit of shifting of the axis and our coordinates. That's simple to do. It's done in the lecture notes if you like to have a look. Do you have questions about this proof using the fourth moment technique?
I could ask just from interest that is there any idea that why this proof has gone into direction to investigate the fourth moment and exactly the fourth moment?
My guess would be that you might first use the second moment and see how things play around. And you see that, okay, second moment is not giving you what you might hope. Then if you have lots of spare time or you're a mathematician, busy mathematician who doesn't have spare time, but anyway wants to do things, so then you might work with third moments. Third moments are not working well because you might do this type of thing with third moments, but and actually with some techniques you could actually, yes, you could improve this to only assume finite third moments. But fourth moments, kind of the trick is that the symmetry with this pairwise power is so nice that you get this upper bound with the fourth moment here. And somehow maybe the same reason why people care so much about variance and standard deviation, because variance is not the natural thing to measure statistical variation. if you think, okay, how much you are deviating from your mean, so the natural thing is would be to use the absolute value, and you would study this. Okay, how much you are deviating from your absolute value, and you might measure your expected absolute difference. So in statistics, this would be the natural measure of how much you are, or that's what you should define as the sigma somehow, like the standard deviation. The kind of proper definition should be this one. But if you look at any statistics textbook, so how do they define this? They define it as the square of this, and then they take a square root. That's what pretty much every statistics textbook does to define, to measure standard deviation. Why do they do that? Is because they put the square, because square is so convenient in computations. It's good for optimization because square is a convex function. So especially square is a convex function. That's how it looks, of course. The absolute value is something which is not differentiable there. Okay, it's convex, but it's not differentiable there. So for some things numerics, so this is more convenient, smoother, and for Gaussian distributions, this is easy to calculate. This is something that you cannot calculate with any technical thing. So because of this type of kind of convenience with even powers, that's the reason why yeah, this is actually the easiest, the simplest possible proof that me and Kalle, that we know how to prove the strong law of large numbers. Assume finite fourth moments and then follow this trick of, I think it's from Kolmogorov. So kind of to get some really easy proof for this. But before we stop, before you run away, so let me say one more thing about this theorem, because actually this is not the best theorem that you can prove. There are much, this is actually a little bit soft version of the theorem. So what's the kind of the big kind of the strong law of large numbers that many people use? So for that law, we assume that x1, x2 are independent. So they are these are mutually independent. Then we only assume that these are in L1. So we assume that these are only in L1, not in L2, not in L4, but just in L1. And then the theorem says that what you want to be true is true. So actually, you can prove it only with L1 assumption here. It's possible to do. We didn't do it in this lecture because it would have taken a bit more time. How to do this one? Extend kind of to get rid of these fourth moments. It's possible to do it, and it's quite amazing that you can do it only with the first moment. What to do is to truncate. So you replace this random variable xj by some xj prime, which is always less than some constant m. And then you prove this theorem when you have a truncated random variable. So then you have bounded fourth moments as well. And then you can use this theorem to get that, okay, the claim is true for the truncated. Then you kind of relax the truncation to get kind of the general theorem. The relaxation is possible to do. If you want to read about it, so I actually might recommend a blog of one of the common, currently living, really great probabilist. His name is Terence Tao. And of course, you know that Terence Tao is a Fields medalist and an amazing mathematician in UCLA, who is working on 8 different or more different fields of math at the same time. But he has a blog. If you go to Terry Tao's blog and you search for what has he written about law of large numbers, so he has described quite nicely how to do this truncation argument and in the blog, if you like to read. And that's the way how to get from this law of large numbers to the really general law of large numbers. And final remark, maybe the game with these fourth moments. Why I wanted to represent it in this lecture is that actually it works for some other algebraic objects. If you want to do kind of network statistics like graphlet counting or like counting how many triangles and are in a large graph. So these type of techniques where you calculate kind of fourth moments or combinatorics. So it can be extended to from just real numbers to, let's say, random graphs.